Okay, thank you for coming. So I will be talking about hacking US traffic control systems. So this is quickly who I'm working for IOActive. I have done several different things in the past, like Windows hacking, ActiveX hacking, web application, database security, lot of different things, and now I'm trying to look at things that affects our daily life, like traffic control systems. So first, I would like to thank a lot of people that provided some comments, feedback, little help, which helped me to save a lot of time sometimes. Also Barnaby, because after a conversation with him, I came up with some ideas about how to target some research, and so he's not anymore with us, but I would like to thank him and remember him. So how all this started? Well, I was trying to focus on some new research because, like I said, I have done different things in the past. Usually sometimes you get bored of doing almost the same research again and again of the same technology. So looking at different technologies, especially some technology that affects our everyday life, becomes more interesting sometimes. So I was looking at some specific devices related with traffic control system. When you go on the road, you probably will see a lot of different and weird devices like cameras, RF readers at the toll collectors, some other antennas. There are a lot of different devices on the road. So I was looking at mostly at the RF readers, the toll collectors. I saw some news that London Traffic Department was going to implement some wireless detection device for traffic control, and that got my attention. So I started to look around that, and I found the provider from the Transport of London, but that it wasn't the maker of the device. So I continued researching, and I found the maker of the device, and it looked interesting technology. But first I had to make sure that the technology was widely used, because if just used in only one place, it doesn't make sense to spend time on researching. So after looking for the vendor name, I started to research some online documentation, papers from the vendor, presentations, news, and I found that it was a very interesting target, and it was widely deployed. It's currently, based on vendor information, there are more than 250 customers in several states in the US and in many countries. But most of the deployments are in the US. Then after the US is the UK, Australia, and Canada. They have bigger deployments too. And then we have countries like Germany, France, even China. Even a city in China has these devices implemented. So there are approximately 500,000 sensors worldwide, most of them in the US. There you have this is a graphic from the vendor, which is Census Network is the name. You can see that it's widely deployed on the US and on main cities, most important cities. Especially in Washington, D.C., there is a big deployment. There are like 1,300 sensors. You even have some location of the devices where they are in the vendor presentation about Washington, D.C. So when I started reading the documentation, I found out that the security word was just once in a 100-page manual. So when you find that, it's like you feel that they will have security problems. So by getting the device, this is not something that you can just buy on eBay or online shopping. It's something that is only bought by some specific resellers which have agreement with the vendor, with the maker, and then by government, by state governments or city governments. So it's not something really easy to get, but we take a chance and send a couple of emails, make some calls. We get some, with a sales guy, say, what do you want the device for? No, we just want a couple. We want to avoid red lights. No, we didn't say that, of course. We try to say a little lie, saying, well, we are going to test the devices because an undisclosed customer wants us to test it. We didn't say there was security testing. We didn't say anything, just that. But it seems that the sales guy wanted to get his commission, make the sale, so we got one sensor and one access point. So it was interesting because I'm from Argentina. I acted from the US, had offices in another country, but at that time when the devices arrived to the office, I was in Puerto Rico, so I got to ship it to Puerto Rico, and then I took the devices back to the US, back to Argentina, back to the US, back to Argentina, back to the US. So I traveled, I don't know how many thousand miles with the devices, making custom without problems, without any issues. So what are these devices? So first we have the wireless sensor, which you can see here, small little device. This goes in the road, so you make a hole. It's supposedly it's very easy to install. Make a hole, put the sensor, and then fill it with epoxy, and it's ready to use. It's a system or a chip. Works. It's a Texas Instrument radio transceiver that works on 802.15.4 protocol standard on the 2.4 gigahertz. So inside it has a microcontroller and it runs Linux. And I don't remember exactly if it is Tiny OS because I lost the initial research notes I had, but I think it was Tiny OS that runs inside the microcontroller. Then we have and this is the sensor opened. You can see there is the electronic board, and below that the batteries. The batteries supposed to work for 10 years, and that is the different layers. So you have the batteries, then the electronic board, and the antenna, and the top. And that's a diagram of the electronic board with the microcontroller, the transceiver, and the magnetoresistive sensor. Because how this works, this is a magnetometer, so it measures the interference of the magnetic field of the Earth. So when a car goes over the sensor, it will detect the anomaly there by the car. So in that way, it detects the cars when go over the sensor. They are magnetometers. Then we have the access point, which is this one I have here, that goes usually on poles next to the traffic lights or other poles around. So this has a core file processor, 4 megabytes of flash, 16 megabytes of RAM, and it runs using Linux. So it runs specific software from the vendor. You can access it over IP, or you can access also over GSM or cellular networks. It is fed by power over Ethernet. It goes connected to the traffic control system. So basically, you get the information from the sensors and connect to the traffic control systems. Then you have repeaters, because there is a limit of range where the communication from the sensor to the access point. So basically, with the repeater, you can extend the range. So when you want to have larger distance between the sensors and the access point, you put repeaters in place, and they can be in tandem too. You can cover several feet with this. So these are the limit of the range. For instance, from the sensors to the access point, you have 150 feet. Then with the repeater, you go to almost 1,000 feet. How this works? So basically, there you have the access point that will get information, the wireless data from the sensor, the detection data, and then in this case, it's an intersection. It will connect to to the traffic controller cabinet, and they use some called contact closure cards, which make an interface between the data from the detection and the traffic controller, in this case for a traffic light. So this is a kind of deployment, for instance, in a ramp, in an access to a freeway. So you have a sensor for detecting the kiwi of cars. Then the present detection, so if there are cars at the top stop bar waiting to go, and then more sensors when the cars go over the stop line. So in a ramp meter, basically they will help on how to set the timing on how fast the cars are allowed to go in the freeway or not. Then in the freeway, you have more wireless sensors too that will measure the traffic there, so they will synchronize also with the ramp meter to say, okay, there isn't much traffic, so put car faster in the freeway. Or it will say, okay, there is a lot of traffic, just put cars very slow in the freeway. So another configuration is at intersections, where you have a stop bar detection with sensors and advanced detection. In this way, they can measure the actual traffic and the cars that are waiting at the light at the intersection. So basically, they can know if in one direction there are many cars waiting or there are a lot of traffic, so they will adjust in real time, for instance, the green light timing. They will say, okay, there is a lot of traffic in this direction, let's make the timing of the green light longer. Instead of 10 seconds, make it 40 seconds. Also, depending on intersection, there are different configurations. Sometimes at late night, they will start flashing if there are no traffic detected, or maybe they will be all red, and just when a car is detected, it will turn green. So there are different configurations. It depends on the intersection. Another configuration is for travel times. So basically, you have a sensor array that when our cars go over it, it will uniquely identify the car. It will make a fingerprint of the car based on the anomaly of the magnetic field. And then after a mile or two, maybe, you get another sensor array that will re-identify the car. In that way, traffic control system can measure the travel time and display the information in the electronic side, for instance, in the freeway. We say, okay, this lane is, I don't know, 60 miles per hour, or you have 5 minutes to this destination, 10 minutes to another destination. That is based on the traffic detection data when the cars are re-identified and the travel time are calculated. So these devices come with some software. So basically you have a Windows software which is used to access the access point. You configure, you access it by Ethernet or some cellular networks, and you can configure the access point and also use the access point to access the sensors and the repeaters in a wireless way. This software is coded in Flash, ActionScript, so it's very easy to reverse engineering to decompile. And with the software, you can send commands to the access point. You can configure different parameters from the sensors, repeater. You can even update the firmware. For the access point, you can update the firmware from the sensors. And then you have software that is to collect all information from different access points and then relay the information to the traffic control systems. So here is a basic diagram. So from the different access points, then you have a Census network, snap servers, which will collect all the information, all the data from the traffic detection, depending on configuration, specific architecture, etc. And then that information is shared for the traffic control systems. And also they have some cloud services, software as a service, which allow you to just connect to the vendor cloud and access your access point worldwide and make some configuration, some stats. You don't have all the functionality, but you can see mostly some stats or detect problems, etc. But I didn't look at that because that's server side, so it will be illegal. So what are the vulnerabilities? So first, there is no encryption at all. So all wireless communication goes in clear text. When I reported this, I got some answer from the vendor. And this was the answer. No, sorry. This is what you find in the manual, in the user manual. So they say that the Sensis Nano Protocol radio transmission, which is how they name the protocol, never carry commands. Only data is transmitted. So while radio communication may be subject to local interference, there is no opportunity to embed malicious instruction to a network device or upstream traffic system, which is crazy. Okay. So that's the only reference to security you find in a 10-page user manual, sorry, in a 100-page user manual. And after I reported the issue, I got this answer from the vendor. I reported it to ICS CERT, and they communicated to the vendor and got back to me. So they said that the option for encrypted was removed because the customer didn't want it. So who is the customer? Governments. So they said there is nothing broken with the devices because it's designed that way, so everything is fine. And also, I told the vendor that the firmware update were not encrypted, but they said, oh, they are encrypted with ICE. So that was the answer. Initially, they also said that the communication were encrypted, but they weren't. So I got very confusing answer from the vendor. Another vulnerability is that no authentication at all. So anyone knowing the protocol or having an access point can connect to a sensor, to any sensor in the world, to any repeater in the world, and make whatever you want. Change the firmware, change the settings, disable it, whatever you want. And also, the access point doesn't authenticate the sensor, so it will be happy to receive data from anything and process it and relay it. And then, like I said, firmware updates are not encrypted nor signed, so just modify the vendor firmware and you can have it updated on all the sensors that are installed, also in the repeaters. So what was the vendor answer? They said that after I said, no, the firmware updates and the communication are not encrypted. So I insisted, it was like, I don't know, many emails with ICS and the vendor say, no, I'm not seeing any encryption here. So they say, we are encrypting, signing the firmware in new sensor version. But there is a small, little and insignificant detail, is that it's not easy to patch this. Basically, you have to dig and replace to patch. So you said they have 500,000 sensors worldwide, so it's digging 500,000 times and replace 500,000 sensors. So, because if you are going to implement signed firmware, encrypted firmware updates, you have to share a key in some way, and if you do it over the air, then you are compromising the key. So I don't see any easy solution for this. And another claim from it's a classic one, so it's unknown protocol, proprietary, so it's pretty safe. So let's see the information about the protocol. So it's implemented over 802.15.4 at physical level. So this is mostly used by Zigbee and some implementation that requires low power consumption and low bandwidth. So it has 16 different channels and work on 2.4 gigahertz and ISM band. And so they have their custom protocol, which they call Sensis Nano Power Protocol, and it's implemented at the MAC level. So it's very similar to the standard MAC for this specification. And basically they simplify it, so it consumes less bandwidth and less power. So for doing this makes the sensor to only listen for communication at specific time slots. So they divide a time frame in, I think it's 64 different time slots. So the access point will say, okay, this sensor should transmit only in this time slot and the other sensor in this other time slot. And the access point will transmit status information every time, also for different sensors, and they get back to the access point every 30 seconds if they don't get any detection. So every 30 seconds, the sensor will send status information to the access point, or if a sensor detects a car, it will instantly send the information back to the access point. So this is a regular packet. First, you have 2 bytes at the beginning, which are used for, are similar to the MAC standard, which is for frame control. Basically, to specify the type of packet. Then you have another byte, which is the sequence number for ordering the different packets. But the access point doesn't care about the sequence number. So you can send anything, and it will be happy to process it. And then you have 2 bytes that are used to identify the sensor, like an address of a specific sensor. Every sensor has a different address with two bytes. And then you have the data. The data is mostly composed of 2 bytes for a specific command, and then the data related to that command. So they have something like this is color code, which is you can configure the access point in a specific color code with 1 byte, and then also the sensors with that same color code. So basically the 1 byte of the address of the access point is the color code, which is shared with some group of sensors. I guess they did this in order to be able to communicate like 10 sensors with 1 access point and have another access point in the same frequency connecting to other sensors and not interference between them. So the data could be from 4 bytes to 50 bytes. It could be longer, but I only observed it up to 50 bytes. So what the sensor sends, the sensor can send information related to the sensor, like the firmware version, detection information, if there is a car detected or not, the mode. There are different modes on how the sensor can work. The battery level also, which is something critical to detect when the sensor is running out of battery. And then from the access point to the sensor, they will send synchronization information to tell the sensor, okay, you have to send data in this time slot or this other time slot. The access point also broadcasts firmware updates to the sensors and repeaters, and different commands for configurations. Some sample packets. This is a sample packet from sensors to an access point. This is a kind of default packet when there is no event. No detection means there is no car. There is no car present over the sensor, or the sensor will send this packet every 30 seconds if it doesn't detect any cars. And this is in count mode because there are different modes. And this is a detection event. You can see there is a different change, which is the last 2 bytes are changes, so this means there is a detection. Sometimes it contains information about timing, so the access point can know what time is correlated with prior detections. And this is information about the sensor. There you can see there are some bytes from the version of the firmware, which is 4C0303. That's the version of the firmware. Then you have information about the battery level, and then about the configuration of the sensor. And the last bytes are used for the whole sensor address. For the communication for the packets, it's only used 2 bytes for the address, but the default address from the maker are 4 bytes, not 2. Then this is a common packet from the access point to the sensor to synchronize or to request status information. So the vendor will provide you with firmware updates, so in a file that has a proprietary format, which is, I don't know, you can see it there, left, right screen. You have a null, then 2 bytes, then a lot of more bytes, and a byte at the end. So the first is a null, it's not used, it's just for the format of the file. And then you have 2 bytes, which is the address of the microprocessor at the sensor. And you have the firmware repeated twice. That is why when the sensor gets the firmware, it will copy the firmware to the memory location that is not currently being used. That means that the memory location that is not running actually the firmware. So they copy to the other, the new firmware to the other address, and then reboot and jump to the new version. And the next update will do the same, but with the other address. So that's why they have two copies of the firmware at different addresses. Then you have, on every line, you have a checksum, which is basically a couple of XORs, very simple checksum, at 1 byte at the end of every line. And then at the beginning, you have 8 bytes, which is a general checksum of the whole firmware, which is also pretty simple, just XORs and some additions. So when you put the access point in firmware update mode from the sensor, basically you just get the file to the access point, and it will start to broadcast it to all the sensors. But after you start broadcasting, you have to set the sensor to listen for firmware updates, which is a specific mode you have to set. So when you do that, the sensor will start getting this broadcast information, and when it gets all the packets, all the firmware, it will update itself. And basically, it's a pretty simple packet because it's just the header information, and then just the command, and then just every line of the file where the firmware is just broadcasted every line over and over again. So in order to do this research, I used some tools. So first, I needed to sniff the wireless data to see if it was encrypted, to learn the protocol, to reverse engineer it. So I got a USB dongle. It's this from Texas Instruments. It's for sniffing 802.15.4. So basically, you just plug it, and it has a software for Windows. You just select the specific radio frequency system, the chip, and then the frequency, and then just start getting the packets. Then I got an evaluation board because I needed to craft a specific packet to send packet to the access point or to the sensor to test communication, to send arbitrary commands, etc. This is the evaluation board. The kit comes with 2 boards, and then you get the USB dongle 2. It has a couple of antennas, and then it has some programmable radio frequency chip. You can easily connect one of these boards to the PC. It has some some program for, you can craft manually packets with it. Let me show you. So this is some, you just choose the board, the chip, and you can just type extra numbers here and manually send packets in that frequency. It's pretty easy to use. Then you have a software for programming the chip, which is basically C code. You have to choose the chip. Then it has some samples you can modify, and you can just write the code and then compile it and upload the firmware, the code is generated to the chip, and execute it with the board, which has a nice LCD screen and some buttons and some joystick here, so it's really nice for doing some tests. So those are the software I just showed. So what's the impact of the attacks? Let me take this. So sorry, I say it's 50,000, not 500,000 sensors. One more zero was in the previous slide. So there are 50,000 sensors worldwide, and I don't know how many repeaters, but all of them currently can be compromised. So you can access them, change the firmware, change the setting, disable them. You can even make them unusable forever, because if you can change the firmware and it's broken, then it won't be able to update itself, and it will be broken. So basically, what you can do, you can cause traffic jams because the traffic control system blindly through the data that is relayed by the access point. So based on that data, they will take wrong decisions, actions. So they will set the wrong timing for the traffic light at the intersection, the wrong timing from the ramp meter. They will show incorrect information at the electronic signs on the freeway, for instance. There are different configurations. Like I said, it could be flashing the lights, more time the green light, all in red. Well, as you know, with traffic, yesterday I had an experience with the cab. I took a cab, and at the exit from the hotel, the traffic light was in red, and it was in red, and it didn't change. So the traffic driver started to get more, how do you say, impatient, and started to pass another car and also pushing and try to cross. And to cross, it continued staying in red. It didn't change for 5 minutes or more. So he just crossed the street and turn and get the way. So basically, when you have people doing this, you can get accidents. That's real. And there are accidents every day with properly functioning traffic control system, but with a small problem, it can be a big problem. So it's not shown here, but for instance, for the Federal Highway Administration Handbook, they explicitly said that problems with sensor can cause accidents. So I'm not making this up. So when I communicated with the vendor, was through ICSR, so they was answering like with lies, because they say no, the communication are encrypted, the firmware is encrypted, but it wasn't, because that was not what I was seeing in my test. I thought maybe in real life deployments, there is a different configuration, and the research I'm doing maybe won't apply it in a real life scenarios. So I have to do some real tests. So what I did was, initially this is power over Ethernet, so I had to make it portable. So with the help of one of the guys from iActive, we make it portable by USB. So I plug it on a USB power supply. And then I also connected to a wireless router, a portable wireless router. So I put this in my backpack, and I connected with my notebook to the access point by the wireless router without any cable. So I was like in Seattle, in New York, in Washington, D.C., just put out my notebook, start pointing the backpack in the right direction to the sensor or to the repeaters, and get the signal there and sniff the traffic, and also try to access the sensors. So it was interesting. Like it's like in New York, nobody cares. You just like a crazy with your notebook in the middle of the street or some corner, and they don't even look at you. But in DC, it was a little weirder, like some spook of some weird people parking in a car, looking at you with glasses, with black glasses, but maybe nothing, but what's weird. Let me show you some video about this. I'm not seeing here. Oh. Okay, so this is Union Station in DC. So this is the ramp exit. I think it's from the parking from the station. And there are a stop bar. So there is a sensor. You can see the mark there. And there is another sensor below the car that is not seen there. And then it is the access point here, just next to the traffic light. So basically that deployment is to detect, because this is a complex intersection, as you can see now. So it's a complex intersection because that is an exit, and then you have 2 streets crossing, so you have like 5 different traffic lights. So basically that kind of deployment is to detect the cars that are waiting there, so it will try to put the green light at some time so the car can go. So it doesn't detect any car, it won't put green there because there is no car waiting. So I was pointing my backpack, you can see there, to the sensors, and I'm using there is the software from the vendor to use the access point, and you can use it also to access the sensors. And all those lines there are sensors. One is my sensor that I already had in my backpack too. And I also was sniffing the wireless data. That is the software for sniffing the wireless data. Those are all the wireless packets from the sensors to the access point and to the access point to the sensor. I just had to set a specific channel in what it was transmitting and start listening the communications. And if I wanted, I could just, there is the other sensor just before the stop bar. So if I wanted, I could just, put a new firmware on those sensors. Maybe I did it, who knows? Or change some settings, and that's it. It's pretty simple. Just need to have the access point or know the protocol. So that's the software. You can see every line here is one sensor, and this is a repeater. These different options, different information that are transmitted over there. So I'm just putting I'm not accessing, modifying anything. I'm just looking at the wireless data, and because I have the software and the access point, it showed me the data in a graphical way and already parsed, so I don't have to do it myself. So we went to another location in DC. So I could access, there was several sensors there, like, I don't know, 10 sensors, repeaters. And you can see there the count information, which is the amount of cars it is detecting. So you can see what's a couple of blocks from the Capitol. And I was with my backpack pointing to the sensors and the repeater, and there is the access point there. And in the opposite, in the other sidewalk, there are the sensors there. That's the repeater. And there is a sensor here. And there is another sensor. Okay, so that's it. So it was interesting. So I could prove that I was right. There was no encryption, no authentication, no security at all. So I was right. Was nice and interesting doing that. So what are the possible attacks? Well, of course you have denial of service, which are simpler because you can just disable the sensors, change the configuration, upload firmware. Like I say, maybe you can permanently break them by changing the firmware. But this kind of attacks are not cool. So a cool attack will be sending fake traffic detection data because there is no authentication, no encryption. So you just need to know the protocol, and you can start sending the fake data to the access point. So you can send fake data mimicking some sensor saying, okay, this direction, there is a lot of traffic. So the access point will get that information and will send it to traffic control system, which will take decisions. So practically you can lie to the access point and it will trust you. The same as stop bars. So if you want to perform an attack, another thing I researched is how to do it in a practical way and very easily. So deployments can be easily located because for one side, the vendor promotes it. So here I have one sample. So here we have James Chicks Jr. from the Chief Traffic Engineer from District of Columbia, Department of Transportation. So basically they talk about the new deployment in DC. And there's something, I'm not seeing this in my, and there is some, you even have a map where they are deployed here. Some nice pictures. And something interesting here, if you can read it. So our initial project considered 122 control stations located throughout the district, and an additional project consisting of 20 additional stations was added along key entry-exit roads of the district at the request and funding of who? Department of Homeland Security. That's interesting, right? Buying and deployment completely unsecure product in Washington, D.C. by DHS, obviously. So you have news where the vendors say, okay, we sold this to this city and they are installing, they're using it. And you have a document from the city Department of Transport, you have a request for proposals, and you have Google Street View, which is very cool because you can go with Google and locate the repeater, the access point, even the sensor that is New York. You can see the sensor right there. So if you want to attack something, just start looking and you will get the exact GPS coordinates where these are located. So we have a problem that the range, the wireless range is not very long, so you have to be at least a maximum of 1,000 feet. So one way of attacking it will be on-site, the attacker going nearby the repeaters of the access point and start sending fake wireless data. So I built an attack. I will show you. I programmed a simple attack. Which here is the board. With that programmed, this is pretty simple sync code you upload to the chip. It has an antenna here, and it has a nice LCD screen. So I put it in my drone because I wanted to test, okay, we can do it from far away, from the sky. Let's see how much the range could be. So I put it in my drone with the elastic band, the board, and fly it. You can see that's cool exploit. You can just set it to send fake data. Just make click, I will start. That is just sending all fake data as detection to the access point. So I was flying the drone at my house. That's the video from the drone. You can see it's already 200 feet. And that is getting all the attack data by the access point, and it's displaying it with the software from the vendor. So I make it to the 650 feet because that's the range of the radio from the drone, but it could be a lot higher, I think. So I make 650 feet. You can see here below where I lost the signal from the drone. And you can see the attack packets are coming and are being get by the access point. And if you look at the sky, you don't even see the drone there. So, and it could be even higher. So I wanted to show the demo here, but this Mac USB network cable doesn't work. It's not working, so I can't show it, but it's pretty simple. So another way to attack would be like putting a device, because this is, it could be this size, I mean, the attacking device. So you attach it, for instance, to a bus in DC, and you have all the stops of the bus to say, okay, this is going to stop in this intersection where deploy the sensors and repeaters. So you just put the attacking device with a GPS, saying, okay, when you are at that location, launch the attack, and that's it. So, like I said, from the drone, then another thing you can do, this is warmable, because once you compromise one sensor with a malicious firmware, because it's radio, it's wireless, it can start replicating to the other sensors. So you can program a worm and make it replicate over all the sensors nearby. Of course, using the repeater to extend the range. What is cool is that it's impossible to know after a sensor is compromised, because the only way to access the sensor is by using the access point, and the sensor is the one that returns information in the protocol about the version, for instance. So you can completely lie with your malicious firmware, can say, okay, this is version number 2, but it's the malware. So it's like once the sensor is compromised, you will have to open it to put some electronics on it, and that's the only way to know, maybe dumping the firmware from the memory. And it will be really complicated because you have to dig. So it was kind of attacks, I would think, like some advanced attack ones. Is because there are some rumors that in the future the smartphone will have Zigbee. And Zigbee uses the same chips, the same radio frequency transceivers. So if a smartphone has Zigbee, once you compromise a smartphone, you can use that person with a compromised smartphone to launch an attack. Of course, this is complex, but it could be done by NSA or someone with an interesting budget. Another attack that was mentioned by Day was because they wanted more blood. They want people killed. So they say, okay, but you can use it to identify cars to trigger some bomb, for instance, because this device can uniquely fingerprint a car. You can sniff some car, capture that wireless data, and then set a bomb in some place. And when the cars go by there, because it's already fingerprinted, you just need to match the fingerprint, and that will be an invisible trigger for the bomb. And because they are in Washington, D.C., you can do with Cadillac One. So that will be interesting knowing that you can fingerprint Cadillac One. So conclusion is one, well, like I said, I'm from Argentina, little town. I could do this research, and as you see, it's not difficult. So anyone from Zero War guy can do it and start launching attack in the US or other countries. So building a attacking device is $100 or less. You just need to know the protocol, then make some simple program and start sending fake data to the access point, and the access point will happily trust the data. And right now there is a lot of buzz sometimes about smart cities. There is a big problem with the smart cities that they are blindly trusting the data that is received by the sensors or different systems. But if you trust blindly the data, then all these systems can be manipulated. Of course, if the systems that they are relying on are insecure. And finally, cyber war is cheap. So I wanted to take just a couple of seconds to let you know about this. It's a community effort. We are working with some guys from US security guys and other guys. So basically it's helping, because with the Internet of threats, Internet of Things, everyone is creating a device, connecting it to internet, and it's being incorporated to our daily life. So it's getting really insecure. Every device you look at is insecure and it's connected to internet. So we are trying to do an effort to help small companies to create secure device. So it's just, if you are interested in this, just go to Build It Securely and you can find more information there. So that's it. I don't know if we have time for questions. I hope you like it. And if we don't have any time for questions, we can talk outside. No problem.
Let's have our questions not threaten the president. I'll go with just who's closest to me for now, because he sat up front.
Where can you find the firmware updates?
Well, I requested it to the vendor because we both have device. Say, okay, give me the firmware update. They say, no, you can't have it because that is used by specialized engineers from our company and say, no, I want it anyways. Say, no, well, okay, you will get a letter for our lawyer. You don't want to give us updates. Say, okay, here you have it. So, but I don't think they are publicly available. So it's like if you buy something from them, but the other software, the software to configure and access the access point and the sensor, that's freely available from the site of the vendor.
Did you get any idea for how, behind the camera, did you get any idea for how good the vehicle fingerprinting is? Would it be able to differentiate vehicles? Could you track an individual vehicle as they pass?
I think it's for, what I have seen is, I think for regular cars. Basically, the vendor said that they can uniquely identify cars and re-identify them. Basically, they rely on that for the travel time part. So basically, you have the sensor here that will identify the car, make a fingerprint, send it to the access point, and then you have several sensors a mile ago. They will re-identify the car by matching the first signature and the actual one. So I don't know how accurate it is, but the vendor is relying on that for one kind of the services that they are providing with this technology.
So you mentioned that the vendor has a fix, but there was some problem in deploying it. And so I'm kind of curious what that problem was. And then the Zigbee standard has encryption built into it. Are the chips that they're using just don't have the encryption, or they just didn't turn it on?
So basically, the vendor has this custom protocol. So it's not Zigbee, it's similar. And they don't have encryption. It's a very simple protocol, and they say that they didn't implement it because the customer didn't want it. Because they, I don't know. Also, they say that in new versions of the sensors, there are encryption on firmware updates. But the problem is that you have to replace existing sensors, because I don't know about a practical solution when you have to share keys with a device. So I don't think there is an easy solution. I mean, they can implement a new protocol, encrypt the updates, but when you update with the new versions, you have to share the key in some way, and that's the weakest point, that I don't think it would be possible without replacing the device. Maybe yes, but I don't think so.
Any other Rave Souls? All right, well, thank you very much.
Thank you.